Thank you for joining. My name's Hefin, and I'm the author of Machine Learning with R, the Tidyverse, and MLR with Manning Publications. I am a life science researcher working at the Francis Crick Institute in London. And today I'm going to show you how to train, tune, and cross-validate a support vector machine model in R using the MLR package. So support vector machines are models for supervised machine learning tasks that could be, for example, for performing classification tasks, where we're trying to predict a set of discrete categories from our training data. Or support vector machines can also actually be used for regression tasks, where we are trying to predict a continuous variable. And both of these are examples of supervised machine learning, because when we present the training data to the algorithm, we give it data that has already been labeled. And so in the case of classification, you give it a set of data, and every case in the data already has a label indicating its membership to one or more classes. And so today I'm going to show you specifically how to train a support vector machine for classification. This is a sort of silly example that I've taken from my book, illustrating what support vector machine models aim to achieve. So support vector machines learn a hyperplane that extends through the feature space that best separates the different classes that you have in your data set. Okay, in this silly example, I've got just two variables. So the money that you made your company this month, for example, and the time that you spent playing games at your desk this month. You're trying to use this data to predict whether your boss is in a good mood or a bad mood with you, which is a very important machine learning task. And in this kind of very simple and contrived example, you can see that actually the classes are very easily separable. And there would be actually many different hyperplanes that could separate these classes perfectly. But the support vector machine algorithm for classification aims to learn the hyperplane that maximizes the margin around itself, that gap that separates the classes. And the reason that this is important is that based on the training data that you have, this will be the hyperplane that will generalize best to new unseen data that maximizes the margin around itself. And support vector machines are very powerful and popular. And one of the reasons that they're so powerful is that they can learn complex non-linear decision boundaries between different classes in a data set. And that sounds like a bit of a contradiction in terms, because I just told you that support vector machines work by learning a hyperplane, which by definition is linear. But support vector machines are one of a set of techniques called kernel methods. And so support vector machines can actually add an additional dimension to your data, to your feature space, called a kernel function, that helps you to separate your different classes. So here's an example where I've got two different variables and with data belonging to two different classes, and there is no linear decision boundary here that could help us separate those two different classes. Okay, but the support vector machine can use a kernel function to add a new dimension to your data set that kind of stretches or deforms your feature space in such a way that now there is a linear hyperplane that exists that is able to separate the classes. And if we were kind of to project where this hyperplane cuts across this kernel function and project that back onto the original feature space, you can see now that by learning a linear hyperplane, the algorithm is actually able to learn a complex curved decision boundary and is able to separate these two classes. Okay, so I'm going to show you in R how to train a support vector machine model. So if you're used to programming in RStudio, then you may know, or you may find it useful to know, that the keys Control, Shift, and R bring up this window that allows you to specify a section. So I'm going to start by loading the packages that I'm going to use for this session. And the first package is the MLR package for performing our machine learning. The second package is, or set of packages, is the tidyverse, which is a collection of packages for data manipulation and plotting that my book discusses in quite a bit of detail. Okay, so next we're going to load the data set that we are going to work with, and the data set that I'm going to work with is the spam data set, which is part of the Kernel package. And this is a data set where every row corresponds to an email and every column corresponds to a variable or a measurement about that email. So it could be, for example, the number of capital letters or the number of URLs. And there is an additional column in this data set that is an annotation as to whether each email was considered to be spam or not spam. And so what we're going to do is train a support vector machine model to try to classify emails as spam or junk mail versus desirable mail, for example. If I check out this data set with the dim function for dimensions, I can see that this data set has just over 4,600 rows and 58 columns or variables. And this isn't a massive data set, but just for the purposes of today, to speed the demonstration up a little bit, I am going to downsample this data set to just 1,000 rows. And then I'm also going to convert it into a tibble. So many people in R are used to working with data frames as a way of storing rectangular data. The tibble is the tidyverse reimagining of the data frame, and we could continue the rest of this demonstration using data frames. That would be fine, but tibbles have a nicer way of printing and presenting the data, so I'm going to use that instead. So I'm going to call my object spam tib for spam tibble. I'm going to use the sample n function to sample randomly 1,000 rows from the data set without replacement. And then I'm going to use the pipe operator to take the result of the function on its left and pass it into the function on its right. So this function is loaded in with when I load the tidyverse. And I'm going to pipe it into the asTibble function just to turn this 1,000 row data frame into a tibble. And now if I just print out this tibble, you can see that it only shows you the number of columns that will fit inside your console, whereas when you print a data frame, it sort of prints everything and you have to scroll up. It lists the columns that couldn't fit on your console, so you can see all of the variables, and it only shows you the first 10 cases in the data set. And another thing that I particularly like is that it shows you the column type, so whether it's a double or a factor or a character, for example. So this is our data set. Another useful function is the glimpse function, and if I wrap my data set in glimpse, this kind of displays the data in a different way. It sort of rotates it on its side so that now the columns are along the left hand side, and it shows you the first several values for the first several cases for every column. And this is a nice way because you can very easily scroll through and see all of the columns that are available to you in the data set. And this is that important variable down here, type, which is a factor that tells us whether each email was considered to be spam or non-spam. And actually, what it might be nice to do is if I give that column to the table function, we can just get a printout of the number of emails within each of those classes. So I've got 619 non-spam emails and 381 spam emails. Okay. So we're going to train a support vector machine model to classify emails into those two groups. So the first thing that we have to do when we're training a machine learning model with the MLR package is to define a task and a learner. Our task is simply a definition of the data that we're working with. And if it's a supervised machine learning task, we have to supply the target variable. Which variable are we trying to predict? And of course, in a classification task, this is a categorical variable. If it was a regression task, it would be a continuous variable. The learner is the definition of what algorithm we're going to use to learn our model. This also includes any additional arguments that we want to supply to control how that algorithm learns. So define task and learner. Okay, so I'm going to create an object called spam task, and the function to make a classification task is make classif task. If I was going to train a regression model, then instead this would be make reg task for regression. If I was training a survival model, it would be make serve task. And if I was training a cluster model, it would be make cluster task, for example. But in this example, this is a classification task. So I use make classif task. And I simply supply the data set I'm going to use as the data argument. So this is spam tib. And because this is a supervised machine learning task, we have labels that we're trying to predict. I supply the variable that we're trying to predict as the target argument. So this is the type variable. And when I run this, MLR will give me a warning that the provided data is not a pure data frame, but from class Tibble df. So the function expects a data frame, so it's giving me this warning. But actually, this does work. You can give the function a Tibble, and everything will continue as normal. So you can safely ignore that message. Okay, so the next thing that we need to do is define our learner. So I'm going to define a learner called SVM for support vector machine, and I use the function make learner. And MLR comes with a large number of machine learning algorithms built in, and you can also define your own if you want to. And all of the algorithms come with a two-part naming system. So every algorithm has a prefix and a suffix. And the prefix determines what kind of task the algorithm is used for, so classification, regression, etc. And the second part, the suffix, is the name of the algorithm. And so if we're performing a classification task, we'll use classif and then dot, and then the name goes as the suffix after the dot or the period. If we were doing a regression, then you've probably worked out it would be reg dot, or it would be cluster dot, etc. So this is a classification task, so classif dot, and for the support vector machine algorithm, it's simply SVM. This prefix suffix is important because some algorithms, just like SVM, can be used for both classification and regression. So this tells MLR that we want to use the classification form of the algorithm. Now there's another optional argument that is useful, and I would suggest that you set, is the argument predict.type. So by default, this argument is set to response. And what this means is that once we have trained our model and we give new data to the model to make predictions on, the model will simply predict the class that it thinks each case belongs to. So in this case, we give it a bunch of new emails, and the model will say this is spam or this is not spam. but it doesn't give us any indication as to how confident the model is as to what the classification should be. And so instead, what I set this to for models or for algorithms that support this is I set this to prob. And so instead, when we train a model like this, when we pass it new emails, instead of just saying spam or not spam, it'll give us a probability based on how likely it thinks that each email is spam or not spam. And this is useful. It helps us make better decisions. It helps us use sort of human in the loop machine learning, because if a model is 99% confident that an email is spam, and that same model is maybe 51% confident that another email is spam, those emails will just be classified as spam, and we don't know that one is more likely than the other. Whereas if we actually inspect the probabilities, then we can create rules such as if you are less than 60% or 55% sure that an email is spam, don't flag it up as spam, or let me manually classify those emails or something like that. So I set this to prob for probability. Okay, so the next thing that I'm going to do is define the way that we are going to tune the hyperparameters of the algorithm. So a hyperparameter is a setting or a variable that controls how an algorithm learns from data, but is something that can't be learned directly from the data itself. So it's something that either we need to set or we need to tune in some kind of experiment. And the support vector machine algorithm has a few hyperparameters that we need to optimize. So I'm going to show you how to do that. Define hyperparameter search space. Okay. So if you're coming to use an algorithm for the first time, you may not already be aware of what hyperparameters it has and which ones you need to set or tune. And so the function get param set from the MLR package will show you all of the available hyperparameters for that particular algorithm. So if I pass this classif.svm, so this prints out the table, and every row in this table is a different hyperparameter, and we get told its type, so whether it's a discrete hyperparameter or numeric or logical. We get told what its default value is, so if we don't touch it, if we don't provide a value or ask MLR to tune the hyperparameter, this is the value that the algorithm will use. We get told the hyperparameter's constraints, so whether it's constrained to be a value between 0 and infinity or negative infinity and infinity, and we get told whether we are able to tune it. So not all of these parameters are actually tunable. Most of them are. And for the SVM algorithm, the most important hyperparameters for you to tune or to set are cost, kernel, degree, and gamma. So let me spend some time explaining what those guys are. Okay, so I already mentioned that the SVM algorithm uses a kernel function to deform or stretch the feature space into a new dimension that helps separate the cases. And how the feature space is deformed and what kind of shape the feature space is deformed into depends on what kernel function we choose. And there are a few different kernel functions that are available to us. And these are some of the most commonly used ones. So one option is the linear kernel, which is actually equivalent to no kernel at all. We can use a polynomial kernel, which is able to create decision boundaries of increasing levels of flexibility. So as you go from second to third to fourth polynomials, you can have very flexible decision boundaries. The radial basis kernel, which is the default, is very, very good at identifying distinct islands of cases that belong to particular classes that may be surrounded by cases in other classes. And actually this here is an example of what a radial basis kernel might look like. And then finally, the sigmoid kernel, which uses the sigmoid function to deform the feature space. And this is sometimes useful if you have situations like this, where you have one class that is sort of bounded by another class on either side. And so our choice of kernel vastly controls the shape of the decision boundary that our final model will learn, and our model will perform better or worse in different situations, depending on which of these kernels that we choose. And so this is a discrete hyperparameter that we need to select. The cost hyperparameter determines how bad it is to have cases inside the margin. So in a perfect situation where there exists a hyperplane that perfectly separates the classes, that hyperplane will have a margin around it that has no cases inside it. Okay, and the further apart two classes that are perfectly separable are, the larger that margin will be. But in reality, in complicated machine learning tasks or problems, it's unlikely that we're going to have easy problems where the classes are fully separable. And so it's very likely that you're going to have classes inside the margin. And the cost hyperparameter tells the algorithm how bad it is to have cases inside the margin. And the trade-off here is that if you set the cost very, very high, then the algorithm will sort of jump through hoops to absolutely try and find a hyperplane that has as few cases in the margin as possible. And what this often results in is finding a hyperplane that overfits the noise that exists near the class boundaries that you're trying to separate. And what this means is that when you try to use your model to classify future data, your model has overfit to the noise in your training set. The other end of this balance is that if you set your cost too low, then your model doesn't really care that much if there are lots of cases inside the margin, and it becomes insensitive to the real patterns that maybe exist in the data near the boundaries of the two classes. And so there's a trade-off here between overfitting and underfitting. The gamma hyperparameter kind of controls how attention-seeking each individual case is in the data set. So if you increase the value of gamma, then every case in the data set is kind of jumping up and down and shouting, me, classify me correctly. Whereas if you set this low, then each case is much less attention-seeking. And so you get a similar kind of trade-off with gamma as you do for the cost hyperparameter. So if you set gamma too high, then you'll start fitting the noise in your training set rather than finding real patterns that will generalize well to future data sets. Whereas again, if you set your gamma too low, then your model will be insensitive to real patterns that exist in your data. Okay. So one way to set hyperparameters would be for you to maybe use some existing knowledge of settings that work well and apply those. But that's kind of a naive approach because it's very unlikely that you're going to pick a combination of those hyperparameters that will result in a model that performs optimally. And so a much better thing to do is to perform a process called hyperparameter tuning, where you allow the models to select a set of hyperparameters that perform the best during the model training process. Okay, and to be able to do this in MLR, it's very simple. But the first thing we need to do is define a hyperparameter search space. So define the range of values that we're going to search across to find that hopefully optimally performing combination of hyperparameters. And so first what I'm going to start off by doing is defining an object called kernels, and this is just going to be a vector of the different kernel functions that I want to try during my tuning process. So this is going to be polynomial, radial, and sigmoid. And notice that I've omitted the linear kernel only because if I include the polynomial kernel and I also include the first degree polynomial, then that is equivalent to the linear kernel. And then actually that's something that I forgot to mention. So I mentioned that we have this degree hyperparameter, and that degree hyperparameter corresponds to the degree of the polynomial. Okay, so if that's 1, then we have a linear polynomial. If it's 2, we have a quadratic polynomial, and if it's 3, we have a cubic polynomial. Okay, and that only applies when we're using the polynomial kernel. Okay, so I'm going to define this vector of kernels, and then to define my hyperparameter search space, I'm going to call this svm param space, and I use the function make param set. And to this function, I simply provide definitions of each hyperparameter and the range of values that I want to search across, and I simply separate each definition by a comma. So I'm going to start with the kernel function as the first hyperparameter. So I'm going to use the function make discrete param, because this is a discrete hyperparameter. It can only take one of these 3 values that I've defined here: polynomial, radial, or sigmoid. So it's a discrete param. The name is kernel, so this corresponds to the name that the SVM algorithm will accept. And the values are equal to kernels. So what I've done is say within the search space that I'm going to search across for my hyperparameter tuning process, I'm going to search across the kernel hyperparameter, and it can take on one of these possible values from this vector here. And now to define my next hyperparameter, I simply separate this with a comma. So the next one I'm going to do is to set up the degree hyperparameter for the polynomial, and this is going to be an integer. So I'm going to search from values between 1, which is the linear kernel, 2 and 3. And I'm not going to go any higher than 3, because the more flexibility that you give to the polynomial, the more likely it is that you're going to start overfitting your training set. So I think 3 is high enough. And for this, I'm going to use make integer param. This is the degree hyperparameter, and this time I need to set the lower bound, which is 1, and the upper bound, which is 3. So my hyperparameter search space is growing. So the next one I'm going to define is the cost hyperparameter. And the cost can take on a floating point number. It doesn't need to be an integer. So I'm going to use the function make numeric param. This is the cost hyperparameter. And I'm going to set the lower value equal to 5 and the upper value equal to 20. And I've chosen these values because of previous experience, knowing that these work well for this particular task. If you're ever unsure, then it can be useful to cast the net wider. It can be a bad idea to restrict yourself too much, because it is quite possible then that you won't end up selecting that optimal set of hyperparameters. And what is also very advisable as well is when you tune your hyperparameters, it's important to visualize your tuning process, to plot the curves, to see whether you actually have ended up with a solution that is at least a local minimum and hopefully a global minimum in terms of reducing the loss of your model. So that's my cost parameter, and then I need another numeric parameter, which is the gamma hyperparameter. For this one, my lower is going to be 0, and my upper is going to be 2. And then I hit that. Oops. There we go. Okay, so I've defined my hyperparameter search space. So when we're training a model, we're going to ask MLR to select values from within that search space and evaluate those combinations of values to find the models that perform the best. But next we have to define how we're going to search that space. So define search procedure. So there are several ways that we can search this space. One option, which is called a grid search, is to take every single possible combination of those hyperparameter values to train a model using each of those values, and then see which model performs the best, which combination of hyperparameters gives you the best performing model. And that is really the only search technique that is guaranteed to select the best model within the hyperparameter search space that you've defined. The problem with it is that if you have even a moderate number of hyperparameters, even if they're all integer or discrete hyperparameters, the search space grows very, very quickly, and so you can end up having to train hundreds or even thousands of models very, very quickly as your hyperparameter search space grows. And in our situation, actually, we would result in having to well, I mean, there are an infinite number of combinations of these hyperparameters because we have these two numeric hyperparameters that can take on floating point numbers. So a grid search really isn't possible in this situation. And so what we can do instead is take on a more pragmatic approach. And one popular, or maybe the simplest pragmatic approach to searching the hyperparameter space is a random search. And a random search is simply where you randomly draw values from the search space. You train a model using that combination of hyperparameter values, and you see how well it performs. And you do that for a fixed number of iterations that you, as the user, can define based on your computational budget. And after all of the iterations have been completed, then you get to select out the best performing combination from all of those samples. And so we're going to define a random search procedure by using the function make tune control random, and we tell it the maximum number of iterations that we want it to perform before it finishes. And really you want to set this based on your computational budget, but higher is better. The more different random combinations of hyperparameters you try, the higher the likelihood that you will result in a set of hyperparameters that gives you an optimally performing model. But for the sake of time today, I'm just going to set this to 20, just so that this demonstration doesn't take a really long time. And other options, so I could have used make tune control grid, would have been a grid search. And another useful one to know about is make tune control iRace, which uses the iterated fRace algorithm for hyperparameter tuning. And this doesn't take as long as a grid search, but is more likely to converge on an optimal solution than just a random search, for example. But today we're just going to stick with the random search. Okay, so whenever you're performing some kind of data-dependent pre-processing step, like hyperparameter tuning or missing value imputation, for example, it's really important that you include that inside your cross-validation when you're validating the performance of your model. And so the next thing that we're going to do is set up the procedure that we're going to use for cross-validation. And I am going to use a procedure called nested cross-validation, and I'll explain what I mean by that in a moment. So define nested cross-validation strategy. Okay, so if you spent any time doing any kind of machine learning, you'll probably be familiar with the training set, validation set, and test set splitting system. And so this idea that it's very important that you never evaluate a model on data that you use to train it, because models almost always perform better on the data that they trained on than on future data sets. And so commonly what people will do is they'll split their data set in two, and they'll call one portion the training set and another portion the test set, and they'll train their model on the training set, and then they'll use that model to make predictions on the test set, and you can compare those predictions with the ground truth to get an idea of how that model would perform when you deploy it on data it's never seen before. And now if you're performing or if you're modifying your model, so if you're, for example, performing hyperparameter tuning, what people will often also do is reserve another portion of their data set that they call the validation set, and they will train a model using the training set with a particular combination of hyperparameters, and then they'll evaluate that model using the validation set, and they'll maybe tweak the hyperparameters, and they'll do that again, change the hyperparameters, do it again. And when they think that they've got a good performing model based on the performance on the validation set, then they will evaluate their final model on the test set, because the model training process has never seen that data. And so that gives you an idea of how your model will perform in future. And for models that either take a very long time to train, or if you've got a large data set, then that technique is perfectly valid, and it's probably the only thing that you can do based on computational budget. But if you have smaller data sets, and or if you have the computational budget, I prefer to use a process called nested cross-validation. So let me show you what I mean. Okay, so in nested cross-validation, we perform an outer loop and an inner loop. So if you imagine that this is the data set that you have available to you, and let's say we use threefold cross-validation. So we split the data into three different folds, and we're going to consider this to be our test set, and this portion to be our training set. Then within the training set, for this particular fold, we again further split the data into a training set and a test set. And we, during our hyperparameter tuning process, randomly select a combination of hyperparameters. And using that combination, we train a model with the training set and we evaluate it on the test set. And then we pick another combination of hyperparameters and we do the same thing. And we do this for all 20 different combinations of hyperparameters in our random search, because remember I set that to 20 iterations. And then of all these 20 different iterations, whichever model performed best on the test set, that combination of hyperparameters is then passed up to this outer loop. And now a model is trained using only the training set, using that combination of hyperparameters, and that is then evaluated on this test set here. And the same thing happens for this fold, except this time we only use the data in this block and this block to form our inner loop. And the same over here, but again this time we use the data from this block and this block to form our inner loop. And by the time you finish this procedure, what you have is three different models evaluated on three different parts of the data that you have available to you, and you can take the the mean performance metric across those three models. Okay, and it didn't have to be 3. You could perform 10-fold cross-validation, and actually even the inner loop could be k-fold cross-validation. It doesn't need to be holdout like we have in this example. And there's a couple of reasons that I like this nested cross-validation. One of them is that we are actually not just relying on a single training test set partition, like the kind of traditional way of splitting a data set. We end up with 3 different models, and we get the average of those in case, probabilistically, we select a test set that has some unusual cases in it. And the other thing is that although we haven't done it in this situation because we're only using simple training and test set split for the inner loop, if we did something more sophisticated like k-fold cross-validation on the inner loop, it means that you actually have a moving validation set. You don't have a constant validation set across the whole model training process, because of course you can end up overfitting to the validation set, whereas this procedure mitigates that. And this might seem complicated, and actually I guess in theory it kind of is, but one of the reasons I like the MLR package is it makes it very easy to set this up, and so that's what I'm going to show you next. And so the first thing that we need to do is define our inner and outer cross-validation procedures. So my inner is going to be, so I'm going to use the function make resample desc for make resample description for a cross-validation procedure. And for my inner, I'm just going to use holdout cross-validation. So just where you reserve a portion of a data set as your test set. And for my split, I'm just going to set this to 2/3. So 2/3 of my data will be for training and 1/3 will be for testing. And then I define my outer cross-validation loop. And again, I use make resample desc. And for this, I'm going to use k-fold cross-validation, which in MLR is just called CV. And for this, I need to tell it the number of folds using the iters argument, and I'm going to set this to 3. And so this here, so 3-fold outer cross-validation and holdout inner cross-validation corresponds to exactly what I've got here. So 3-fold for the outer and simple holdout for the inner. Other forms that I could have used LOO for leave one out cross-validation. I could have used rep CV for repeated cross-validation, which is the same as cross-validation, but after every round you randomly shuffle all the data and you perform k-fold cross-validation again for as many iterations as you define, and also subsample as well for subsampling. So the next thing that we have to do to actually get this tuning and cross-validation process joined together is to create or to use a wrapper function in MLR to combine together the SVM algorithm with the tuning process. So wrap together SVM with tuning. So I'm going to create a new learner called SVM wrapper, and I'm going to use the function make tune wrapper, and to this I give the name of the learner, which is our SVM algorithm that we defined earlier. I'm going to give our resampling argument for the actual tuning procedure itself, which is inner. So this is going to be our holdout cross-validation. So this means that for every combination of hyperparameters, use holdout cross-validation to evaluate how the model performs. The parset argument is where we tell the function what our hyperparameter search space is. So this is equal to SVM param space, that I defined here. And finally, I need to tell it how we're going to search that parameter space. And this is with the random search that we defined earlier on. So I define my wrapper. And then finally, all that's left for me to do is to actually perform the cross-validation procedure. And this includes the hyperparameter tuning process. So I'm going to create an object called CV with tuning, cross-validation with tuning. And to perform cross-validation with MLR, we use the resample function. And to the learner argument, we give our wrapped learner. So this now becomes a learner in its own right. We tell it the task, which is our spam task that we defined. So we're trying to predict whether emails are spam or non-spam. We tell it the resampling procedure, and this is the outer threefold cross-validation procedure that we defined. And there's an additional argument which you might find useful, which is models equals true. So by default, this is false. So we'll perform this tuning procedure, and if this is false, it'll give us just the performance metrics and nothing else. If we set this to true, it'll give us the performance metrics for each model, and it'll also retain the model information as well. So if you want to interrogate or use each individual model, then you can do that. And so if I hit Control and Enter, this starts the training procedure. So this is for the first fold of our outer k-fold cross-validation. And you'll see that for each combination of hyperparameters that the tuning process selects, we also get a value of this statistic called MMCE, which stands for mean misclassification error, which is 1 minus the accuracy, basically. So it's finished doing one outer cross-validation, and we ended up with that combination of hyperparameters. And the final MMCE value for that iteration. And then it moves on to the second fold of the outer cross-validation loop. And again, does another 20 iterations of 20 random combinations of hyperparameters. And then it'll do the final one, and then it will give us the aggregated mean misclassification error, the mean of those three values. Okay, so it's told us that the best performing combination, as judged by a tuning procedure, was the polynomial kernel with degree 1, so basically the linear kernel, cost of 14.6, gamma of 1.68, and this was the result of that final of the third iteration of that outer k-fold cross-validation. But the aggregated result across all three of those models is an MMCE value of 0.099, which is, so in terms of accuracy, is around 90%, which isn't too bad for a quick first attempt. Okay, so say now you've cross-validated the procedure that you intended to use to train the model, and you're happy with how you think that model will perform on new data based on how it performed in your cross-validation strategy. So now what you would do is you use all of the data available to you to train the model, because a model trained with more data always has less, or usually has less bias. And so now I'm going to train the model using all the data, including the hyperparameter tuning process that we just performed. Okay, so train model on all data. So first we're going to perform the tuning procedure to get the best performing set of hyperparameters. So I'm going to define an object called tuned SVM pars, and the function tune params allows you to tune hyperparameters in isolation outside of cross validation. And the learner again is our SVM. Task again equals the spam task. Resampling is inner, so we're just going to use holdout cross validation for every single combination of hyperparameters. The par set is equal to svm param space that we defined, and the control is rand search. And you'll notice that this is very similar to what we did back up here, but now you can think of this bit as simply doing this inner loop, but using all of the data instead of all of the data up here, and using only a portion of the whole data set as its test set. Okay, so I can run this, and again this will, for just 20 iterations, randomly select combinations of hyperparameter values, evaluate the model on the test set, and return the combination that performs the best. And what we can do is then take that set of learned best hyperparameters and create a new SVM learner that has those hyperparameters. Okay, so you can see actually that this time we ended up with a slightly different combination of hyperparameters, possibly because the number of iterations that I'm using is quite low. So our final tuned SVM model is going to use, so I'm going to use the set hyperpars function, which takes a learner and a list of hyperparameter values and simply smushes them together, so that you end up with that learner with that set of hyperparameters. And so from this object that we just defined here, that has the result of our tuning process, I'm going to extract X, which has a list of each of the returned hyperparameter values that were selected during our tuning process. Okay, so then now all we have left to do is to actually train our model. So we have our learner with the set of defined hyperparameters. Now we're going to combine that with our data and actually train a model that we can use to make predictions with. So tuned SVM model, and we're going to use the train function. And we're going to take this learner that has the tuned hyperparameters, and we're going to combine it with our task. And in a couple of seconds, right, so now we have our tuned model. So we've used the SVM algorithm with that tuned set of hyperparameters to learn a model that will predict whether the emails are spam or not spam. And now that we have our model, we can use it to predict new data. And we can do that with the predict function, where we give it the name of the model, and we give it new data using the new data argument. And this is usually a bad idea, but what I'm going to do is just pass the data set that we trained the algorithm or the model with back into the model to see what it predicts. And so if the data that you gave it already has the target variable in it, then you'll get this one column telling you the truth. So what the actual value is of the new data, and then you see this response, which is what the model has predicted each email to be. So you can see here that the truth is spam, the response is spam. It got that one correct, but in row 2 you see the truth was spam, but actually the model predicted that it was non-spam. And this is why earlier on, if you remember, I suggested that you set your learner predict type equal to prob, because now we have two columns, one for each class, telling us the estimated probability that each email belongs to either of the classes. And this is useful because, for example, this email here, the model was only 54% confident that email was spam. And you may want to handle that differently to an email that the model is 90% confident that it was spam, for example. Okay, so that was basically all that I wanted to show you today. So let me go through a quick summary of what we've done. So we simply loaded our data that contained rows corresponding to emails and columns corresponding to measurements on those emails. And that dataset was annotated to tell us whether the emails were spam or not spam. We then defined our task, which was the definition of the data and the variable that we were trying to predict, because it was a supervised machine learning task. And we defined our learner, which was the algorithm that we were going to use. We defined the hyperparameter search space that we were going to use to tune our model. We defined how we were going to search that space. So we chose a random search, but we could have chosen a grid search or used the iterated F-race algorithm, for example. We defined our nested cross-validation strategy. So we use threefold outer cross-validation and holdout inner cross-validation. We wrapped together the SVM algorithm with the tuning procedure so that we could cross-validate the whole process together. And then we actually performed the cross-validation. And then because we were happy with how we thought that our model training procedure would perform, we trained, we tuned the hyperparameters on all of the data available to us, and then trained the model on our entire data set. Because when you do that, you result in, you're training a model with more data, and so you create models that have less bias. And the very last thing that we did was use our model to predict the emails of an imaginary new data set. Okay, so if anyone has any questions, I'm happy to stick around and answer them. Or if not, then probably the best place to get hold of me is on Twitter. And you can get me, my Twitter handle is HRJ21.